Okay, thanks all for coming. We are very, very privileged today to have Dr. Hanle Holdiman. Hope I don't feel a lot. Feel free to read the name. So he has many, many, many years of experience on integration of variable renewable energy resources from a research institute in Finland, VTT. Then now you've left PTT. You had also some experience abroad, visiting institutes in Portugal, the US as well, and you have been really the driving force behind the IEA Task 25, which has published a lot of high impact influential papers on integration of renewable resources. So we are very, very happy to have you here. And a warm welcome. Okay.
I'm in the middle.
Okay.
I think it's before it up.
Yeah, he's watched it before. Okay, so this IA, you know what that stands for? International Energy Agency. So they have a big office in Paris making all these global studies, but they also have what are called TCPs, technological collaboration programs, and for all the different energy forms like wind. And then these ones are like just not really meeting in Paris, but they are sort of governmental collaboration between countries. And then they launch research tasks. And this task started in 2006. And it has a long name, Design and Operation of Energy Systems with large amounts of variable generation. And we also collaborate with our solar TCP task. And then we have tried to filter in all the experience that all the experts have for wind integration studies, wind and solar integration studies. And more recently, coming like general power system studies. So let me see, which should I here? Okay. So this recommended practices report that is just out, I'll talk about generally why we do this, what kind of report it is, and then it has these chapters for recommendations for input data, for adequacy, for operational impact, and stability, and finally just recommendations how to present results and a summary. So this is my presentation today. It has a lot of slides, but we don't really need to go through them in detail because the slides is also like having these lists of recommendations which can be used later on. So, okay. So why do we make this report? We make also reports summarizing results of different studies, but this is only about methodology to provide all the researchers, also system operators, with information how to make these studies, how to model and simulate power systems so that they have a lot of wind and solar there. And okay, we have these recommendations as sort of checklists, and you can also use this as a benchmark for any study, just to say, okay, what all did I take into account and what I didn't, because even if most of the simulation models can basically take into account everything, but then there are always practical limits on how much detail you can put there. So basically, it's about methodologies, it's about assumptions, it's about inputs, but no results in this. So there are other reports, summaries, articles that we do that actually summarize results. So we don't have any results here. And this is the third edition that we are already doing. So we've been updating this. And it's okay. In 2018, we have edition 2 actually adding solar as well, and something about distribution grids. There's not very much about that, but we did add a section on that. Now we have a bit simplified flowchart on how we go through the report. Each of these boxes is a chapter in the report. And also it needs updating because the first edition we made, 2013, then when we talked about studying power systems with wind and solar, then we actually talked about 10% share of wind, 20 was so hot. And then in 2018, we were like, okay, we need to do some more. We start seeing studies with 30% wind. And that now, of course, a third layer comes. We have wind and solar dominated systems. I'm not saying like 100% wind and solar because those are a bit rare. But generally, when we start having wind and solar as more than 50% share annually, this means that sometimes it's 100%. And then you also need to take that into account. So basically, this flow chart is that first you have to set up your study. Like, okay, what kind of scenario you want to study, how your power system works, what is the links to other energy sectors in your model. And basically you could study a future scenario and you would make like feasibility checks. You check if the operational impacts is okay, whether hour to hour it works. You can check that your resource adequacy is okay. You have enough generation capacity for all possible load hours, and you have enough transmission, for example. And then you can also check the dynamics, so the power system stability after possible faults in the system. Is it still okay? So this can be thought of as 3 different feasibility studies. And of course, you may only concentrate on, okay, this study is only to check the future resource adequacy, or this study is only to check for some possible future stability issues, or we are only looking at whether operationally the dispatch works. So not all the studies do everything. And then we try to show that there are actually a lot of iterations. If you want to do everything, you may want to go back and change something in your assumptions for the system design. Now, would you say now that you are doing some of or part of these boxes in your research? Yes. Are you doing operational? Dynamics, yeah. Resource adequacy? Anybody doing that or no? Yeah? Okay. And are some of you actually doing more than one box? Or are you, usually I would say the students would, or when you make your research, you would focus on one of these.
Also doing a bit linking of dynamics with steady state operation.
That's right,
So
yeah.
that integrated.
Yeah. Yeah, that's right. Okay, so one big thing that we noticed was not much talked about in the 2018 edition of recommended practices was the energy system coupling. So that is becoming more and more important for the future power systems. Even if we concentrate a lot on power system side, modeling the system couplings becomes important. And this is trying to show that, okay, blue thing is the power system part. So what are the flexibility coming from different storage buffers here with these black bubbles here? So we do have hydropower with storage. We start having more and more battery storage as well in the system. And in future systems, we can have things like compressed air energy storage as well. And then we start having direct electrification, for example, the transport sector, which can a little bit also have flexibility to two sides in the future with the grid. And then we start having access on the batteries in electric vehicles. We can also start getting power to heat. And then we start having thermal storage, for example, access to thermal storage. Also, seeing that when you do your power system simulations, you need to take into account also that, for example, I come from Finland. Helsinki, our capital, has been relying on combined heat and power for district heating of Helsinki, coming a lot from coal. And now they have to shut down coal. So what are they doing? They are buying these huge heat pumps, and they are converting a big old oil cabin to a thermal storage. And that's just happening. It's not like anybody giving them money to do that. It's just like, okay, if we want to get rid of coal and we have district heating system, that's the most efficient way to do that. There will be something burned as well, biomass, a little bit, waste and things like that, but it's tiny compared. It was, really in the conventional power plants before. So this kind of power to something with a storage buffer, we really see it already happening. And in future, we start having more and more, even industry with different processes could have storage buffers there. But sometimes then the industry doesn't use electricity, but they take it from whatever storage there is. And this is just a picture from Denmark, where they look how they see towards 2050 and how their demand, which is now quite small here, less than 50 terawatt hours a year, how they see it evolve. And they just put, okay, most of the current demand is fixed also in future. And then some of it is like partly flexible. But a lot of the new demand is potentially really flexible. But it is potentially because, we need to check. So like data centers is a bit of a problem to really push them to be flexible, whereas many others, hydrogen derivatives, will probably be operated in a way that when there's scarcity of wind and solar, they will not operate. So they will be, it's a different type of thing. And then another thing generally is that we have these model tools that are quite different. If you try to model something for policy and planning, and then when you start going toward techno-economic plant performance and unit commitment, and this is normally what these studies would do, but they are somehow linked to the policy targets, and then checking whether it works out, and then you go to network power flow and system stability, and often we do see at least some linkages or some inputs coming from the, higher level models. What we don't see so much is that there would be a feedback coming from the more detailed studies up. And of course, system stability, linking that to power flow, the steady state, that is something that is being done more and more, but actually really going back to, for example, capacity expansion tools and those to see that, hey, we checked and this scenario actually had issues with feasibility and actually going back. But this is something that needs to be done more and more when we have higher shares of wind and solar, or then jumping in different way to say that, okay, for stability reasons, you need to change your policy. Yeah, maybe in future. Okay, then I start going through the recommendations. So there's a lot of text and all this, but just for you to see what's in this report. So we try to then, there's a lot of pages about input data, especially how to simulate wind and solar generation, how to simulate the forecast errors in future systems coming from wind and solar. So a lot of details and references we try to collect of how to best do that. And then we try to, write also about other inputs, and then so you can see different inputs here as rows for wind and solar, for load, for the network, and for the other power plants. And then for the different model tools, what is that, trying to summarize in just a couple of words, like what is it that you really need? Is it like the time resolution, hourly at least, or preferably more? Or then, taking more like snapshots to look at dynamics, and how to choose those ones. And then first, you just need the generation time series. For some, you need also the forecast time series. And then you start needing like, okay, active and reactive power capabilities. So this is the way we try to summarize a lot of detail that we have in those things. And we have added a note this time about climate change when you model, because it's not just wind and solar, it's hydro data, and it's also your load data that will be, well, anything that is weather dependent in future. So there's already efforts to actually, and there are many people saying that when you start modeling just 10 years ahead, you need to look at climate change. However, there are also many people saying that, there is still some issues with this model data. So we know now quite well, we already have existing aggregated power system level wind data that for the time series, for the forecast time series, that we have checked and we know how it goes. So to have the smoothing impact, for example, for wind. But for the future climate model data, we don't know yet how well they then produce wind and solar data, for example. So we just say, okay, don't just jump and trust the climate data. Be a bit cautious and also run the simulations with the best possible data you have now, without looking at the climate change impact that may change it, at least for you to sort of know how you go. And also, what is still happening is the technology impact. So there was a big jump for wind power plants coming from yearly average capacity factors being between 20 and 30%, that they are now between 30 and 40%. And that's a huge impact on also for really notable, significant impact in the time series. So if you use old data with the technology, you also have a different data series coming. And for solar data also, there are things, and also how they use these things, like for solar power plants, for example, since they are so cheap nowadays, you can even put them to roofs that are facing north or east and west, where you don't get as much yearly generation as the ones facing south, but you get it in times when it's more valuable. So that's being done, and then it will start impacting your time series. And for wind, we anticipate that at some point it makes sense to buy turbines when you're adding more and more wind turbines, that some of the turbines that you're adding actually start being so-called extremely low wind turbines, that they will shut down when there's a lot of wind, because then, the grid is full of wind energy and the value starts dropping. But they will try to get as much wind as generation as possible from the low wind speeds. It's not much, but it's valuable. So that's why we probably start seeing also this kind of things happening with the technology. And of course, when you're simulating future, like 10, 20, 30 years from now, somehow it's good if you can at least think about whether in your power system this may also have an impact. Generally about the scenarios and how you do the scenarios. So previously, a lot of them were just done by assumptions. So just took the existing system and, okay, we know that they are now planning these and these new power plants, and we know that these and these power plants will be taken out of the grid as they go old. And just the load projection was just like, okay, we know from previous data it's increasing 3% a year or something like that. And we knew something about the transmission expansion and the assumptions of generation load and storage. It was pretty much as it was operated today, but you can, of course, also try to just make these assumptions. However, when you start seeing more and more wind and solar, you really need to start using capacity expansion tools to make your scenario in the first place, to optimize and make sure you have all the assumptions and lifetime of assets there. You can include then emission targets and make different scenarios with same emissions, for example. And you can, the capacity expansion tools can also optimize transmission between the areas. And more and more needs to take also the energy system coupling into account. And what is really important for future is how you assume that the new load, for example, whether it will be flexible or not. So somehow including the operational practices may also be important. So generally we recommend for when you set up your scenarios, that if you just have a small, there are sometimes countries, most European countries have wind and solar already, but if you go elsewhere in the world, there are still countries that are just starting. They are doing their first studies. What are the impacts of wind and solar? They are adding shorter amounts of wind and solar. It's just short term, for example, running, how it will be in a couple of years. So then it's okay. You just add it to the existing system, just make the foreseeable changes. But as soon as you start getting larger shares, you need to change something. It's just not having this system and plus wind and solar. You also need to change the remaining system. And then you start seeing the recommendation for capacity expansion tools. And if you have a future wind and solar dominated systems, you just need to use those, because the systems to study will be very different. And also new electrification happens at the same time, and IBR in inverter-based resources have changes needed in the system as well. All due to reduction of synchronous machines, there will be changes needed, and then this energy system coupling will come. And then also, you really need to do all the different checks of operational resource adequacy and stability to make sure that your future system is feasible. Okay, so this was like main thing. Yeah. And now I have like chapters on the main feasibility check. So this was a lot about how to actually do the scenario and what you need to think about for the input data. So first, it's here the resource adequacy. So resource adequacy is a term actually that often people think that this includes both capacity adequacy, generation capacity adequacy, including storage, and the transmission adequacy, the network adequacy. And some people think it also includes flexibility adequacy. So it can basically include everything. But the model tools that we have traditionally would look more about the metrics and methods to check that your generation capacity is sufficient. And then it's like really look cross-border. It's not, we can have island systems, but very many systems, they do have interconnection capacity. So this is also relevant to take into account, as well as cross-sector, not just electricity. And then one thing that was traditionally always talked about a lot was capacity value. So when we add wind and solar, what's the capacity value? And when we add more and more of them, what's the marginal addition that they add to the capacity value, which is decreasing over time. And then for the network adequacy, that's normally what the system operators do in the transmission planning. But we have just given some ideas what you need to keep in mind when you have a lot of wind. And the results that we're looking here, it's like loss of load expectancy, loss of load probability, energy not served, expected energy not served, these kinds of low level of ends metrics. And many studies try to also still look at the capacity value of the wind and solar. And just cutting this very short of the chapter, it's just, this is the kind of recommendation list that we have for resource adequacy, mostly looking at the generation capacity adequacy. So first of all, your results will be extremely dependent on what you assume of neighboring areas. This is what we have seen from the study results that we have looked through. So if there are import possibilities, of course, then it's always the question, if I include all of those possibilities, it's like overestimating. And if I don't include them, then it's like really underestimating what the real situation will be. But you can try to do it somehow, either including forced outage rates or really look at the times of generation scarcity more in detail with a larger area. And here we also have we are also moving from traditional loss of load probability calculation to actually run unit commitment and dispatch with Monte Carlo. And one other thing is then the interannual resource variability. So you need a lot of years of data to be able to do this. And we had a nice example from Ireland a long time ago where they actually showed that after you included 7 years of data, no matter what 7 years you took, you get about the same results. But that was Ireland. So then we tried the same for Finland, and it was like 17 years it's you need. And then what they do in France, they say, no, you need more than 30 years. Otherwise, we don't trust the results. So you really, you want to capture the extreme events. But of course, also, what is the probability of them? And then in future, it's not just having enough capacity, it's more about energy adequacy. So the hydro-dominated systems, they have always thought about, there's enough capacity in Norway to produce whatever extreme situation, but it doesn't matter if there is no water in the reservoirs. So they really need to look at the energy adequacy more in detail when there's hydro-dominated systems. But the same starts coming when more and more of your annual energy is coming from wind and solar, then it's also about energy more than just looking at capacity numbers. And here the climate change impacts then start coming because they impact everything to do with weather. And yeah, I already mentioned a little bit about this moving to chronological models. And this is to do with flexibility, to be able to include the flexibility at times of scarcity of energy, then you need to study this chronologically and not just do this traditional way of calculating the loss of load probability for a system. And also to look at different metrics, not just take one metric and see how it goes, but start looking unserved energy, the scarcity events. You can have the same loss of load probability, but the event can be, either many hours but not much loss, or then not many hours but a huge loss. And it's like you need to start looking also in the metrics that they are different. Yeah.
Yeah, I have a question. I wanted to ask you about the first point a little bit more. So what is the trend that you're seeing within the adequacy studies regarding the import possibilities? Is it the overestimation or underestimation of import? Because I realize sometimes in the academic studies, what I see is the push to include the import more because this could be considered as a potential resource in times of scarcity. But then you go to the individual system operator studies, and they often are aware or afraid of including or overestimating import because they are more kind of nation focused and they want to be adequate without help of any other surrounding care. So what is the trend?
So Europe is here. I actually have this European example here. So ENTSO-E is doing this resource adequacy assessment in Europe so that they include all the neighbors. They look at the whole of Europe. And they are all the time, they do this like every year, and all the time they are improving what they they have the database, wind and solar, hydro, temperature, and they have the market coupling with net transfer capacities, going towards flow-based as well. They have the demand for different countries. And then they start looking at these sort of in Monte Carlo and trying to just do this and check how it looks like for different countries inside an interconnected system. But I don't think anybody else does it that well than Europe. Europe is really pushing this. And I think this was also a policy push, because if all the different European countries would do this separately, we would over-dimension all the systems. We would have a lot of extra backup that would probably result in a lot of fossil-fired power plants not taking out, just keeping them, and then ending up, either paying them extra or even running them extra to keep them alive. And then it starts conflicting with European targets for emissions. So that's why Europe is really, I think this is a really great thing that they are doing in Europe, but other parts of the globe, they don't really do this anymore. Yes, they are still, then the metrics are still calculated. I mean, even if they study this, they do the simulation. And this is more like how they do it. They have the time series, they have the outages, which is the Monte Carlo, like just at what time the forced outages will happen. And then they finally have 35 climate years and 15 time series of non-availability of the thermal generation units. And then they get the adequacy metrics, and I think I did, yeah. So then the results are like this. So every country has these different ones. Loss of load expectation in blue, loss of load duration, and then they also do the P50, P95, so 50th and 95th percentile. One in a 2 years event or one in 20 years event, how it looks like. So 1 in 2 years event is in orange, and then in gray, you see this sort of 1 in 20 years event when you start seeing several countries having problem or sort of having the numbers. Here is something like 50 hours on average, 50 hours per year. On average, when you start including in your data set this sort of 1 in 20 years event. So yeah, even if you model it, so then this means that all these countries have modeled it taking into account the neighboring countries, and then they see what is the problem in my country, because then the simulation will see scarcity in other countries happening at the same time. So there is no the market that would allow power to flow to that country.
Yes, but if I may, one thing is that ERA is not a binding document, right? So the fact that NCO is actually modeling it, it doesn't really enforce any specific actions from the member state. And the second comment is that it is also extremely compromised because this is a European Union level document.
Yeah.
It is not a pure academic study. It includes a lot of compromises so that the potential capacity expansion and the transmission expansion recommendation that ERA is providing fits all the member states. And like behind the scenes, what I heard, it is extremely difficult to actually obtain that with a pure model run. And unfortunately, what they're doing, and like the beauty of it, okay, we have this document that encompasses all the member states, but the drawback is that we have to satisfy the needs and agree and have an agreement across all the member states, which is usually extremely difficult to do.
Yeah, I think one thing that where Europe is sort of trying to reinforce this methodology is that if a country says that we want to have a capacity mechanism, for example, we want to pay our coal or gas power plants this much extra, they have to prove that the calculation is not just their country as an island, but it's a country taking. So they are sort of pushing a European-wide methodology if you want to do different policy in your country. So somehow I think they are still trying to link it, but sure, it's work in progress. And even just, thinking about, like they see all the time, they do it every year, and they always see like, oh, we need to start take this and that into account. So it's a process that is evolving, that they already see that, okay, we get different results because we would need to have larger number of scenarios and sensitivities, and should we have annual resolution, should we have this and that. So it's like they also produce that do these scenarios respect national projections, union-wide and national energy policy targets? So I guess this is really the difficulty. There is not one European Union policy. There are also the national policies. But yeah, it adds complication, doesn't it? And then related is when you start looking at capacity value. So basically you do a similar calculation and then you check that adding a marginal amount of wind, what's the benefit? How your loss of load, keeping the loss of load probability the same, how much you can add load. And that would be, that megawatt number is the real, benefit that this marginal addition of wind and solar will bring. And of course, this is really system dependent. If anything changes in your system, you need to run it again. And also this, as it's more and more wind and solar, of course, they will eat out this benefit because they are so correlated. So adding same of a correlated thing, you can't get, more value after some point, or you can get very small marginal value after some point. And there has been previously this ELCC method, effective load carrying capability. So you calculate the loss of load probability, and then you add wind, and you see how much load you can add with wind to keep the same loss of load probability. So that's like the method. And but this is okay when you look at smaller amounts of wind, and when you start having higher amounts, you need to use other types of Monte Carlo methods. So chronology. So the same things actually come for generally about resource adequacy. Also, when you look at only capacity value of wind. And of course, here you need to have your, as in any of these studies, you always need to have the data synchronous. So all the weather data needs to be synchronized to that weather. So wind, PV load becomes synchronous. And at some point, I don't know whether a capacity value for separate technologies is meaningful anymore. So I don't actually know whether these studies are even being made anymore in Europe, for example. Are we already past this? For transmission planning, there is not very much in this report, so we just try to highlight some things because transmission system operators have this transmission planning, and they actually will go through also, they will make scenarios, they will check that the scenarios have resource adequacy and that they work operationally, and then they see how much transmission is worth building, and they need to then make a cost benefit assessment to prove that it's really worthy of making this investment. And usually for a lot of wind, it's always economically beneficial to build more transmission because of the smoothing impact of wind. And it looks like for solar, it's pretty much the same because it does help for solar integration as well, even if solar is more concentrated on the same hours of the day on a large area. So we basically try to just bring out a couple of recommendations, like you need more scenarios than you used to do. They did a lot of things just looking at high load and low load situations, winter, summer situations, just a couple of snapshots to check it works. So now it's getting more complicated. And then, of course, there are also other enhancement options. You can just go and reinforce transmission lines. But there are sometimes that's not, I mean, it can take a lot of time to get building permits for that, but you can also invest in different grid enhancing technologies. It's not the same, but in many cases, it will actually help a lot. And then basically you do need combined power flow analysis and this unit commitment. Economic dispatch or simulation runs to really see also the dynamic line rating as one enhancing technology or other, how they really benefit as an alternative for upgrading. Here are just, some recommendations from his part. You would need to check the power flow cases to study with snapshots. You would need to look at the statistical relevance of the cases and really capturing the variability of the year with dispatch decisions, how wind and solar will impact the dispatch decisions when checking what snapshots to look at, or even in many cases, you would do it for all of the years. And then you would have the deterministic steady state setup, the power flow analysis to look at whether there are bottlenecks, whether the voltage profile is okay, and you need to do a bit more network modeling improvements to really analyze some of these grid enhancing technologies like dynamic line rating. And then for weak grids, often here you would also do short circuit level analysis. And there are currently more and more of these tools available, like screening tools, looking at the grid strength across the network. So grid strength is also becoming more, it's just not only the stability part, but also coming here. Okay, this was about the resource adequacy, and then the next one is any questions, more questions here before we go on?
one-way flow that you're presenting the slide. How you can do, you mentioned you want to do some feedback, how that thing is going to be your feedback. You go to the previous slide. One. Very nicely, one-way flow. I guess you also need to feedback to make work.
Yeah, this is, well, actually the recommendation checklist is just a list of bullet points. But so these arrows are not very meaningful. It's just a list of bullet points of just recommendations. When you do this, take into account for the cases to study, this is what to take into account. When you do this, this is usually you would do it in this order, I guess. But I mean,
Or if you go just a bit level, it's not.
yeah, I think mainly the sort of mainly it's like whether you would need to go back in the beginning to modify your inputs, or whether you would go whether you would do it, between these boxes. But there can be many ways to get it right, or many iterations that you would need to do if you want to have the whole picture actually.
But we know how we make changes. I mean, I guess if not, it's failed. We know we need to make changes. But how do we know which is the direction we should make the changes? The guidance, for example, what particular stability.
Yeah, well,
what changes we need to make.
so for example, if the loss of load probability becomes really high, you need to go back and add either peaking capacity, backup capacity, or add storage, or add flexibility in your load, or you need to do something and then check whether, or then also if you start seeing that, hey, when you study this scenario, there will be huge bottlenecks here and here, then you can check whether the breaking enhancement technologies work, and then you can say, okay, with these things, it's okay. Or then you go back and say the transmission grid needs to be different. So this is like one way of doing it.
Wondering if just an indication that the results are not okay is already an improvement to current methods, because usually you have just a one stream, right? Like you conduct one of these elements and you don't check, right?
Yeah.
Because you focus only on one part. So probably just checking it with the others, with dynamics, with operational impact, and saying, okay, something is not right here, but we don't yet know or have capabilities to go back and feedback it. Probably already an improvement to some extent, right?
Yeah, that's
or
right.
not politically really relevant, because then someone can say, okay, it's not correct, then why are we doing that?
They do check where the connect in the US. They go down to the border. They have exactly the problem. Like if it doesn't work, what to do next.
But are they transparent with indicating that what, for example, their capacity plan is showing? Do they say, oh, but it actually can be not dynamically appropriate?
The one we find that values should be okay.
Probably they don't tell about all the iterations they made, but there can still be a lot of iterations that they've actually made and checked. Like this ENSO-E makes this 10-year network development plan, and that's also, they are checking more and more things every they do it every 2 years, and always they are evolving the methodology to take more and more into account. And of course, one thing, I mean, if you make a study, it's just that if you don't do any of these checks, you can just say that we assume that there is enough flexibility in our scenario. So it's okay, we didn't check it, but that's the assumption we make. And then at least you're transparent that, I didn't check it, but this is my assumption for this scenario. So it's like, instead of saying that, or then you say that we checked it up to this point and it did work. But that's also interesting. I mean, would be very nice if people, when they whatever future scenarios they make, if they would also say that, you know, these ones we actually checked that it works, and these ones we didn't. This is just an assumption that in future systems, for example, the IBRs, the grid forming technology will take care of all the stability problems. They didn't check it because that's our assumption. But at least you say it instead of just, you know, saying that we made this scenario and it just works perfectly. Yeah. So then the next thing is to ensure that the scenario is operable. So that's a lot to do with flexibility, looking at the variability, looking at the uncertainty, the forecast errors, and also then having some extreme events there would be good. And then you would have a unit commitment economic dispatch tool, and really to simulate what the impact of wind and solar is on the operation of the other power plants. And what we see is that these results are very sensitive to a base case selection. So if you want to study what's the impact of wind and solar, then what you have chosen as your base case reference will pretty much determine your impact. So basically, if you see a problem with wind and solar, and if you go back and iterate and do changes in your operational practices, do changes in your flexibility assumptions, then you can make it work. And then this is often done with 1 year of hourly data in the past. And of course, in future, it's better to do it like quarterly or 5-minute time resolution, and also having several years that have, for example, high wind year, low wind year, because this also has impact. If you just take an average weather year, you will not see all the impacts. So basically, for managing your variability and uncertainty, so you can do it partly by scheduling. So like the variability between the intervals or the time resolution intervals, like if you go from hourly to 5-minute, you also take a lot of the variability by having a faster scheduling and dispatch. And then, but you always need to have reserves, the operating reserves there. But it's really like, if you have shorter scheduling intervals, you need less operating reserve. If you do hourly dispatch, then inside the hour, you need to have a lot of reserves, operating reserves, to deal what's happening inside the hour. So basically, I think this is a lot trying to say that these are sort of linked, that because they were the starting point often for a wind integration study was to say that how much wind will impact the operating reserves. We need to carry more operating reserves when we add wind. But it's not just about that. It's also when you change something in your operational practices, your scheduling intervals, that's also another way of dealing with that. So here again, a recommendation list is provided with a lot of bullet points, and some of the bullet points are about the time series, that all the weather-dependent sources should have the same weather year as a starting point, and the forecast uncertainty should also be paired with the same weather. And then, if you have a lot of hydro, then looking at wet and dry years makes a lot of sense. And then the base case scenario, if you do comparisons, so if this is the aim of your study, that you will really try to capture the impacts of wind and solar, then the choice of base case is important, and capacity expansion models are then needed to make also these base case scenarios good. And then finally, for the unit commitment models, when you have higher shares of wind and solar, you really need to look at also the forecast errors, because often these models are just run deterministic. but some kind of stochastic optimization, rolling planning to take into account that the day ahead forecast errors are quite big and uncertainty is big, but then when you are closer to the time, then it's less uncertainty. So this needs to be taken into account. And what is really important then are the capabilities and the limits of flexibility that you want to capture also the limits. Here neighboring systems is also important. And for example, for hydropower, it's often a bit of a problem to model then. They are often modeled like too flexible because they are extremely flexible, but they do have some limits. And then other relevant energy sectors are coming here. Grid constraints is something that can impact a lot because otherwise, if you have the transmission grid available, you can take a lot of problems out by just that. And then finally, the operating reserves that you put in your model also you need to check with wind and solar. But since they are often for different timescales, you need to be sure that you're not double counting, having the same variability impact for different timescales of reserves. And then finally dynamics. There are a lot of different stability issues, and this is of course also then power system dependent what to study. So what are, as a starting point, what are the particular system concerns that you have? But basically, you want to determine if the grid is sufficiently robust. And you need to check the dynamic impacts and investigate also locationally how it goes. And the transmission limits are sometimes set by a combination of different stability phenomena for that system. And here, optimal measures. Also, there's often generation curtailment happening that you can have because of these dynamic constraints coming from stability. So you could summarize this in a way that for selecting cases, you should do some in future systems with a lot of wind. You should do some initial screening. And then based on the unit commitment and economic dispatch, you should there sort of take the snapshots. And then all these models, dynamic models of wind power plants, solar power plants, battery energy system, and also load in future should be suitable for each of the particular stability. And then basically what stability cases to take. So I know I'm at the end of my time. I'm just showing you that there are some other slides because I go through, different recommendations for the different stability studies, but not going there now. Just saying that for the results, the iterations really are important. And if you are making any comparisons to a base case, that's very important to mention how you do that and how you chose that. And it's always a very good idea to present the share of wind and solar, the size of the power system, and if you have any curtailments happening, because that's often the impact of wind and solar. And then all the relevant assumptions from these checklists. And we really hope that this checklist are useful when you make just for benchmarking, just to say that from this list, these things were taken into account. So hopefully this will be okay. And I think by now you know that all these studies are built on many inputs and assumptions, hopefully very transparent. And if you have really high shares of wind, then you should do all the checks for your scenarios. But if you have less wind and solar, then you can perhaps for example, skip the stability. This is something about the future things. You have large areas, more complexity. Your demand and storage will look different. Integrated models are happening, and even the reliability could be thought of differently in future. And this is just acknowledgements for the people working on this paper. Thank you. So thanks also for posing questions during the work. I think it's always nicer to present that way. But if you have any more questions. Yeah.
Is there any recommendation about how to consider interaction with distribution systems?
This is something that we were really hoping to get, but I didn't get very good input for that section in this report from the group of experts that was working here. I think that's also a lot of work in progress at the moment. It's also becoming more important.